Mueller, and I'm the Director of Applications for the AFM business at Bruker. And I'd like to welcome you to this installment of the Bruker AFM webinar series. This presentation today is titled Nanoscale Mechanical Property Measurements in AFM Modes with Direct Force Control. It will be presented jointly by Dr. Gheorghe from NIST and Dr. Bede Pittenger from Bruker. Before I introduce Gheorghe and Bede, I'd like to make a few quick logistical comments. First, we encourage your participation during the webinar. If you have a question, please type it into the questions dialog box on your screen. We will accumulate these questions to the presentation, group them together, and answer them at the end of the prepared remarks. Quite often we have more questions than we can answer in the session, and in those cases we will be sure to follow up with answers via email afterwards. Also, if you'd like to review the presentation afterwards or pass it on to a colleague, the webinar will be posted online within a week in the webinar section of the Bruker webpage. As a follow-up to this presentation, you'll also be receiving an email with this link. Finally, when you exit the webinar software, you'll be asked to take a brief survey. We'd very much appreciate if you take the time to complete this, as it helps us pick the topics that are most important to you and generally make the series better. So let's get started, and let me introduce the presenters of this joint webinar. Dr. Gheorghe is a research scientist in the Materials Measurement Science Division of the National Institute of Standards and Technology in Gaithersburg, Maryland. He received his Ph.D.s in physics from the University of Bucharest in 2000 and Colorado State University in 2005. Since 2005, he worked at NIST on developing new scanning probe microscopy techniques for nanoscale material property measurements. In particular, his efforts are focused on quantitative measurements of elastic properties of materials at the nanoscale by dynamic scanning probe microscopy techniques such as contact resonance atomic force microscopy. Dr. Stan has more than 30 publications in the field of nanoscale material science. Dr. Bede Pittenger is a senior development scientist in the AFM unit of Bruker's Nanosurfaces division. He received his Ph.D. in physics from the University of Washington in 2000, but has worked with scanning probe microscopes for more than 20 years, building systems, developing techniques, and studying properties of materials at the nanoscale. His work has spanned topics from studies of interfacial melting of ice to material property mapping of polymers. Dr. Pittenger has more than 20 publications and 3 patents on various techniques and applications of scanning probe microscopy. So I'll first turn it over to Bede to begin his presentation titled Nanoscale Mechanical Property Measurements in AFM Modes with Direct Force Control. Bede?
Thanks for the introduction, Thomas. Today I'll be discussing mechanical property mapping with force curves as an introduction to this presentation. And but before we get into the details of this, let's give you a little bit of background on AFM. Recently, there's been a trend which has been transitioning from mapping topography with AFM only and into mapping topography along with other information channels. But way back in 1986, contact mode was developed, and in this mode, initially it was just topography. And the Z piezo was adjusted in order to keep the cantilever deflection constant while scanning. The downside was that the lateral force on the tip was uncontrolled, and this could lead to tip and sample damage. Tapping mode made this method more gentle by looking at the amplitude of the cantilever vibration near resonance. Since the tip isn't in contact 100% of the time, the lateral force is eliminated, and you get much more gentle imaging of soft materials, and you have a better chance to preserve a very sharp tip. At about the same time as tapping mode was developed, researchers were looking to expand beyond the topographic imaging and use the AFM probe to learn more about the properties of the samples at the nanoscale. They already knew that they could use force curves to study the sample by ramping the Z position of the sample and looking at the cantilever deflection at a single point. They realized that if they could collect force curves at every pixel in an image, they could map the tip sample forces while keeping the lateral force to a minimum, because again, we are fully retracting after each pixel is collected before we move laterally. Unfortunately, this force volume mode is relatively slow, and it makes images with a lot of pixels impractical. Contact resonance imaging is much faster than force volume, but it uses contact mode and remains in contact 100% of the time, so it is not as general as tapping or force volume. In 2009, we developed peak force Q&M to allow the benefits of force volume with much higher ramp rates, and this allows much higher scan rates. Then in 2011 and 2012, peak force tapping, which is the actual mode of control, which is keeping our maximum force during the ramping constant. This peak force tapping mode was applied to traditionally contact mode techniques like tuna, providing unique benefits in both in these cases. Recently, we launched peak force IR with our new Inspire product, which combines peak force tapping with IR imaging, SNOM imaging. And later in this webinar, we will discuss recent progress to extend the capabilities of peak force Q&M and contact resonance. So comparing peak force Q&M and force volume in a little bit more detail, force volume, again, was developed first, and it's based on regular linear ramping. Basically, you have linear ramping of the Z piezo position, and instead of in peak force Q&M, where we have sinusoidal ramping, this is one of the key parts of the peak force Q&M capability. That Z motion being sinusoidal helps the system to avoid having any piezo resonances or overshoot in the measurement. In these plots, I've got the Z motion with the dashed line here showing the sinusoidal motion over one period, and linear ramp in the case of force volume, and then down below here we have the deflection signal. So initially you're out of contact, not touching the surface, and then here at this point you go into contact, then you're in contact up until this point, and then basically out of contact again, and that whole process takes a millisecond or maybe a little less in peak force tapping mode or peak force Q&M. While in force volume, that would be happening in a second or a tenth of a second. Now, another major difference is that peak force tapping has a real feedback loop force control. So there's an actual benefit. Each curve can benefit from what happened in the prior curve. It works the same way that like tapping mode feedback works and contact mode feedback works, in that we pick off the peak force, but the feedback loop knows about what happened previously. In force volume, basically what's happening is every time you do one of these ramps, the system is attempting to turn around as soon as it sees the force exceed a certain level. And that means that pretty much every time it fails, and it will always overshoot a little bit. It's just a matter of how much it's overshooting. And then basically the bottom line is that we can get up to much faster ramp rates with peak force Q&M, but in force volume it's very limited. And so essentially for imaging, we get much better force control with peak force Q&M, faster ramp speed, higher imaging resolution, and the force stability is excellent. Whereas with force volume, we have options. We can choose one of these options. We can either have it be fairly quick, fairly fast scanning with high resolution, but poor force control and poor Z accuracy, which means your property maps may not be very accurate. Or you could have good force control, but very slow. It could be several hours to take an image. Or you could have fast and good force control, but very few pixels. So this is what most people end up doing, is they want it to take a reasonable amount of time and still get good force curves, so they end up going to maps that only have like 16 pixels or something like that, So, or 16 by 16. So here's actually an example of some peak force Q&M data. This is a little video that shows the high spatial resolution and force control of peak force tapping. And you can see the image actually being generated in the movie. And here's the force curves that are happening. And this is actually atomic resolution on mica using the dimension large sample AFM. And I want you to notice how stable the peak force is here during the acquisition, and that the force curves are being acquired simultaneously, and we can actually process those in real time so we can get maps of the material properties in real time while we're imaging. So for peak force Q&M and force volume, we have the whole force curve in both cases of these cases. So we can basically process the data very similarly for the two techniques. It's just a matter of during the analysis you change from a sinusoidal Z position to a linear, and that's basically it. Once you've actually taken this first step and you've converted from the Z position and deflection versus time, converted it into deflection versus Z position, then at that point the maps are pretty much the same, or the curves are the same. So they can be processed in the same way. And we have code to allow us to do that, basically, and generate the separation plot, and then from the separation plot we fit the curve to get modulus. We can also get dissipation, adhesion, peak force, and deformation out of these maps. So now one of the key things about both of these techniques is that the feedback in both cases is based on the peak force. Although, as I said before, especially when you go to higher ramp rates, the accuracy is going to be much higher on peak force Q&M because of the way the feedback loop works and benefiting from the previous curves. This protects the tip and sample. This is unlike some of the other modes where we actually don't have a good comparison between the baseline force and the peak force, like contact mode, or in tapping mode where the feedback is really based on dissipation as well as peak force. And the other thing about both of these techniques is that we acquire all a curve for every pixel in the image. So both in force volume and in peak force Q&M with peak force capture functionality, we can capture all of the curves, and so they can be analyzed with different models offline. So when do you need high resolution and quantitative property information? This is kind of a maybe not obvious, but one area is when you design or if you want to understand composite materials, because the details of the properties and structures at boundaries within composites are actually a critical function to the behavior of the system at the macro scale. So, and as we go to smaller and smaller composites, these structures become more and more important. In this case, or here I'm showing one example of a situation where this could be useful. This is actually a cross-section of a heat sealable bag, something like that you might have, you might, when you buy potato chips or tortilla chips like you get down here in California, they would come in one of these heat sealable bags. And the idea is that you, during the manufacture of the bag, it is folded over upon itself, heated up, and that causes the sealant layer to bond to itself. So the sealant layers are folded so that they touch one another. And then this barrier layer here is the part that actually keeps the chips fresh, because that's what keeps the gas out, the moisture out of the bag. And then this tie layer is really important because it allows the two layers to still stay together once you've bonded everything together. Otherwise, it would delaminate. So in this image here, we're looking at the modulus map of this interface between the barrier and tie layers in the heat sealable bag. And you can see basically several things here. Basically, you can see that there's a relatively abrupt junction here that's happening, and basically between the two materials. This is because the polymers are relatively incompatible, and this is giving you an interface of around 75 nanometers. If you look at a single scan line, you can see that it really drops off very quickly. This is 75 nanometer drop. If we look at an average over this, we see that on average there's that drop, but then there's another little structure here that's happening. And that's in this area here. You can see that there's lamella that are not crossing the profile from one component to another, but they're growing epitaxially from the barrier layer. And those go for around 250 nanometers into the tie layer. They're highly ordered in this area, and then they become disordered in this part. And the reason for this modulus changing here is likely because of these things being so ordered. And the length scale of that of the lamella is thought to be determined by the linear segment length of the polymer during processing. If we look at the other interface, the interface between the tie layer and the sealant layer, the first thing we notice is that we have a very good cryo microtome of this sample, and that really there is no signal of any change happening in the height map. So the topography is not allowing us to actually even see where this boundary is. But if we look at the modulus map, then it clearly shows up in the average. We see that essentially the individual lamella are still very sharp and they're narrow. But if you look at the average here over the image, again you see a drop, and this drop is happening on a range of a couple hundred nanometers to around a micron. And you can also see that some of the lamella actually cross over from the tie layer into the barrier layer, and that can actually go. They can go for up to about a micron into the sealant layer. Sorry. So that's one of the reasons that this works so well, is that basically the tie layer is very well connected to the sealant layer. Now, if I look at the actual force curves and in these two different layers, if I look at the barrier and tie layers, you can see that there's a lot more hysteresis in the part that's in the tie layer And that actually shows up in our dissipation map, because what it's doing is it calculates out the area between the approach and retract curves. And sometimes this is dominated by adhesion, but not so in this case, because the adhesion is roughly the same for these two. It's just the tie layer is got more hysteresis. And so we believe what's going on here is that there's actually a difference in the dissipation within the material, or a viscoelastic signature of the tie layer that's showing up here. When we do our modulus calculations, we don't have an inelastic deformation mechanism in that calculation. It's just the DMT model, so it wouldn't show up necessarily in the modulus, but we can see it from the dissipation channel here. Now, how should we analyze these force curves for viscoelasticity? We know that the hysteresis is related to the viscoelasticity, but it's not easily calculable because the deformation rate is changing during the ramp, and this happens because the contact area is changing. This is kind of a known problem with indentation type measurements. But to get a feeling for qualitatively how force curves might behave at different ramp rates with a viscoelastic material, we looked at using the Bede simulator to actually calculate out what some force curves would look like given a generalized Maxwell model of isotactic polypropylene. So we took data from this Reed paper here, where we have storage and loss modulus as a function of frequency, and this green line is actually the room temperature line. We did a Prony fit of this, which fills in the components of the Maxwell model, and then we're able to use the Bede simulator to calculate out what the force curves should look like. And basically, you see that right away that basically there's two things that are happening with these force curves as we increase the ramp rate. For one thing, these are getting steeper, so the apparent modulus is increasing if we were to calculate the modulus for each of these curves, we would see that it was increasing, even though it's the same material. The other thing that we see is that there is kind of a larger hysteresis at around 100 kilohertz, and also the 1 kilohertz is actually fairly large hysteresis also. So somewhere in between, say, 100 and 1 is probably a maximum in the amount of hysteresis. That seems to correspond to a maximum in the loss modulus, which kind of makes sense. So basically, we can expect those two things to change if we were to do some experiments and look at things as a function of ramp rate. So what I've done is I went ahead and I did some measurements using both force volume, which allows me, as I mentioned earlier, to do lower ramp rates, and peak force Q&M. And so I started out at 0.5 hertz with force volume images, and these are all individual images. So we have 8 images here, 4 in force volume. And you can see I used a lower pixel count so that I was able to have this take a reasonable amount of time. And I increased the ramp rate up to 2 kilohertz with peak force Q&M. And you can see that the color of the polystyrene part, this kind of light pink area, is roughly the same for all of the curves. But if you look at the LDPE part of this sample, this circle, it's actually getting to be a darker purple as we go down to lower ramp rates. And so basically you can look at the average of these areas and put it into a plot, and you see that basically our force volume and peak force tapping data for polystyrene, all is roughly about the same value. Whereas with LDPE, I'm actually increasing as I go to higher ramp rates. That's similar to what the polypropylene suggested that it would do. So, and actually, this is a log-log plot, so this is actually increasing by about a factor of 3 over that frequency range. Now, what if we wanted to extend to even higher frequencies? Well, we could use contact resonance to do that, and this is contact resonance frequencies are typically in the 100 to 1,000 kilohertz range, which nicely complements the lower frequency ranges of peak force tapping and force volume. Contact resonance can work with multiple eigenmodes of the same probe, which allows both better sensitivity to stiff samples, but also it allows you to work with multiple frequencies with the same probe. Contact resonance can also be used to get viscoelastic properties directly. You can look at this paper by Yuya, Hurley, and Turner in 2008. The problem with contact resonance for polymers is that it is a contact mode technique, so it suffers from the uncontrolled lateral forces that we talked about earlier between the tip and the sample. Also, the vertical force between the tip and sample are susceptible to variation because what will sometimes happen is the background deflection where you're not in contact can vary a little bit if there's some variation in room temperature or in electrostatic force between the tip and the sample. That would be a long-range electrostatic force. So the result here is that if we look at, this is a PS2MMA sample, we can see in contact mode that we have a reasonable image, but it's not as sharp as the one in peak force tapping. And this is because either the sample is being worn or scratched, or the tip just picks up some material from the sample, and that causes the tip geometry to change. So note that there's some really small features in here. If you zoom in, you can see that there's even smaller features, and these are down to even like below 10 nanometers. And you definitely would not see that in the contact mode image. So the other thing that can happen is that we can also get an unstable property signal if the tip sample contact area starts to vary too much, and that basically is not a problem with peak force tapping where we're keeping the tip sharp the whole time. So basically the question arises, could contact resonance be combined with peak force tapping? And basically we've combined it in several cases previously. We have this peak force tuna mode. This is actually a map with conductivity and height showing vertically standing carbon nanotubes, which definitely would be impossible in contact mode. Here's a KPFM, peak force KPFM map where we analyzed the work function around a sample. You can also get these very high resolution stiffness maps down to the atomic level, or now with this Inspire, peak force IR, we can get an IR absorption or reflection map. This is a PSP&A sample again. And these are all combining other techniques with peak force tapping, and so you get better performance of the integrated technique because the peak force tapping is at lower frequencies than, say, if you were to try to integrate these with tapping mode. Also, peak force tapping works with pretty much any probe, allowing the probe to be optimized for the maximum signal in the technique. You don't have to use stiff probes in order to avoid adhesion issues like you do in tapping mode. And then also peak force tapping provides simultaneous quantifiable material properties along with the new thing that you're adding. So you really get some additional benefit there. So these four examples demonstrate areas where we have productized new modes. In addition, some researchers are working at the leading edge of AFM and using our signal access to create their own extensions, building on peak force tapping. So the question arises, what about peak force tapping and contact resonance? Could you combine them using our open signal access and thereby capture the benefits of each? So with that, I'd like to summarize and wrap this up, but basically the bottom line is that force spectra-based modes can measure modulus in a huge range, going from live cells up to fused silica. We focus on modulus for this talk, but there's other property maps such as adhesion, dissipation, and deformation that are also available. Property maps can be very useful in identifying and understanding the structures of material interfaces, and often the topography is not enough. This is another view of that interface where we were not even able to see the interface at all from the height map, but the modulus gives us an exact position of it. And peak force QNM has the speed to allow acquisition of high-resolution property maps in a reasonable amount of time, while force volume allows comparison to slower ramp rates. Together, these two techniques allow a wide range of ramp rates needed to study the time-dependent effects. But while it's clear that the apparent modulus can be influenced by the viscoelasticity, we need to do further work to fully connect the viscoelastic behavior observed to the available models. Contact resonance can help by expanding the range of frequencies further and by providing simultaneous storage and loss modulus. However, contact resonance does not work well when scanning soft materials like polymers. So what about combining contact resonance and peak force tapping? And I'm going to now turn this over to Dr. Gheorghe Stan, who will take a look at just that possibility. Thank you.
Thank you, Bede. In the second part of the talk, I will cover a few aspects related with contact resonance AFM practice and some of its applications, especially from the point of view of force control in various CR-AFM implementations. The message that I am trying to convey here is that the force control gives us a fine-tuned knob for a better localization in the space of measurements. But let's start with the basics. Briefly, in contact resonance AFM, an AFM tip is brought into contact with a surface at a given applied force, and while in contact, it is mechanically vibrated by a small amplitude oscillation at one of the eigenmode frequency of the cantilever tip sample system. Here are showing the two most common configurations. One is with modulation applied at the end of the cantilever by the piezo shaker of the AFM, and this configuration was introduced by Yamanaka and Nakano as ultrasonic atomic force microscopy in 1996. The other one is with modulation applied underneath the sample and was introduced by Rabe, Jenser, and Arnold as atomic force acoustic microscopy, also in 1996. And intuitively, we can look at the elastic tip sample contact like a spring attached at the end of the cantilever, and this tip sample contact spring modifies the boundary condition at the end of the cantilever and induces a shift in the resonance frequency of the cantilever, so modifies the dynamics of the cantilever. Of course, the contact representation becomes more complex if we have to consider the damping, lateral couplings, and so forth. But for elastic modulus measurements, what we are looking primarily is to measure the shift in the resonance frequency of the eigenmodes of the cantilever from the free values to the contact value, and then use a clamp spring coupled beam model to convert these resonance frequency shifts into the contact stiffness. The next step is to go from contact stiffness to the elastic modulus of the sample, and this is done by using the contact mechanical model that we think is most appropriate for our tip sample contact. So a simple representation here is with a Hertz model, a spherical tip indenting a flat surface. The contact stiffness is proportional with the diameter of contact, the reduced elastic modulus. This reduced elastic modulus is a combination between the indentation moduli of the sample and the tip. The indentation modulus finally is given in terms of Young modulus and Poisson ratio. But we have a couple of unknowns here, like tip radius. We don't measure directly the contact radius. So a way to bypass some of the unknown parameters, like tip radius, contact radius, cantilever stiffness, and ultimately also to minimize the uncertainties introduced by an appropriate description of the actual contact mechanics, is to perform successive measurements on a reference material and on the test material, take the ratio of the contact stiffnesses that we measure, and determine the indentation modulus of the sample with respect to the indentation modulus of the reference material. Here, a reference material means a material with known elastic modulus, either from calculations or other type of measurements. And even better measurements can be accomplished when we use two reference materials with elastic moduli that bracket the elastic modulus of the test material. The question is why we need contact resonance, because we already have force distance curve measurements, and basically we are looking at the same parameter, contact stiffness. And the answer is that with contact resonance, we can extend the range of the elastic moduli that we can measure. And the hint is showing here in this plot of sensitivities of the two techniques. Here we have with the black curve is the sensitivity of the force distance curve as a function of normalized contact stiffness. And we see that this decays much rapidly with the increasing contact stiffness compared with contact resonance sensitivity here for the first two eigenmodes. And it's common for, it's known in force distance measurements that in order to do measurements on stiffer materials, we have to increase the cantilever stiffness, because then we push the measurement point in the sensitivity, in the region with higher sensitivity. But with contact resonance, this sensitivity, measurement sensitivity decays much slower, so we can look at stiffer materials with medium stiff cantilevers. And an experimental illustration is showing here as what I just explained. If we look at the force distances, we see good sensitivity. They have different slopes here for compliant materials, up to 10 gigapascal, but we don't see any difference between measurements on fused silica and silicon with this medium stiff cantilever. However, if we do contact resonance with the same cantilever on a bunch of different materials, in between silicon and fused silica, we observed a bunch of other materials that we can measure, and this is in terms of sensitivity of contact stiffness, not necessarily elastic moduli. Here are different low-K dielectric materials of different thicknesses and different elastic moduli. But the idea is that we have better sensitivity in between these two stiff materials. Now, once we understand and control the dynamics and contact geometry of CR-AFM, we can look at different materials and structures. Here is showing an example of mapping copper low-K dielectric interconnects. The structure is showing schematically here with copper lines isolated from separated from low-K dielectric by a thin tantalum nitride diffusion barrier. We have topography, contact resonance frequency, and amplitude maps made at different applied loads. The image topography remains unchanged as the load varies, but we have substantial differences in both contact resonance frequency and amplitude between these three materials at each applied force. If we look at the color bar scales here and the contrast, the color contrast is different at different loads. So if we use copper here as a reference material and calculate the elastic modulus of low-K dielectric material, and also we combine the frequency and amplitude measurements to look at the dissipative contribution to the tip sample contact coupling in terms of contact dynamics. So here is showing the contact resonance amplitude versus the applied force, and we were able to resolve the decay of damping in the nearby subsurface region of the two materials. An example is more complicated contact geometry showing here on a granular gold film, and in this case, during scanning, the tip sample contact experienced significant changes in terms of contact area size and number of contacts. The contact is in form of single asperity contact on top of the grains and in form of a multiple asperity contact in between the grains when the tip comes in contact with the adjacent grains. The way to calculate the elastic modulus map was to, after the contact resonance was made, we image the area in STM to get a more accurate topography and combine these two images in the following way. We simulated the tip coming in contact with at a given location and push into contact until the apply load and the measured contact stiffness were recovered, and at that point observe what was the contact area and then calculate the elastic modulus. So what we see here in the elastic modulus map is that we observe a consistent decrease, about 20% of the elastic modulus in the intergrain regions compared with the grain regions and associated with intergrain softening with the orientation mismatch between adjacent grains. And it's interesting because if we look at the contact resonance map, we have higher values for the resonance frequency in intergrain regions, which means higher contact stiffnesses, but not necessarily higher modulus. Being a contact AFM mode, the tip condition requires a lot of attention during measurements, both in point measurements and scanning. And a direct way to assess the tip wear is to image the tip before and after use, like by SEM or TM, but this might not be available all the time. So an indirect way is to repeat the same contact stiffness measurements on a given material and observe if there are significant changes in the measured contact resonance frequencies, because these changes will indicate a change in the contact area solely. But another way to look at the problem is to take advantage of this and work with a pre-wear tip shape. And here is showing an intentionally flattened AFM tip that was using contact resonance AFM measurements on a series of low-K dielectric thin films. The tip was pre-flattened on a silicon surface at loads higher than any loads used in subsequent measurements. We were sure that no extra flattening was produced during measurements, so the probe was actually behaving as a circular flat punch. The flatten here is produced at about 12 degrees with respect to the cantilever orientation due to the tilt of the cantilever in the holder. With such a flattened probe, we performed load-dependent CRFM measurements, which consisted of recording simultaneously both the deflection and resonance frequency of an FM cantilever as this is brought gradually in and out of contact. And unlike CRFM measurements made at only one applied force, Low-dependent CRFM measurements have the benefit of detailing the force or depth dependence of the contact stiffness over the entire contact regions, with a better validation of the involved contact mechanics. Here is showing an example of such measurement on a silicon surface, and we observe that the contact resonance frequency remains unchanged once the contact is formed, and this is a clear signature of the flat punch behavior. Here I'll show you a LabVIEW interface where we acquire simultaneously the force distance curve measurements. It's in this window. In the lower one, it's showing the resonance frequency peak as it's shifting at higher and higher values as the tip comes into contact and push into contact. And here are collected the values of the contact resonance. So at full contact, we see that we have this plateau where the resonance frequency remains unchanged, which means that having a constant, we have a constant contact radius, so the contact stiffness is directly related with the elastic modulus, with relative elastic modulus, and then we can extract very easily the elastic modulus of the sample from here. And we have the reverse response when the tip is coming out of contact. Here the frequency spectrum is showing again the free resonance was the second eigenmode of the cantilever around 1 megahertz. One immediate extension of this low dependency RFM measurement is to perform them into an array distributed over the scan area, in which case we end up with a new scanning mode, namely intermittent contact resonance AFM. And the idea is that the volume of this data will provide the three-dimensional characterization of the nearby subsurface mechanical properties of the material probe. And not negligible, it is also the thing that being operated in an intermittent contact mode, the tip is better preserved during scanning than in contact mode. Here is showing implementation in force volume. And to get quantitative measurements out of this technique, we are looking for a few key requirements. We need force control during intermittent contacts. This can be achieved in force volume, peak force taping. We also need adhesive force measurements to be used in the subsequent analyses. We also want to be able to correlate the force and resonance frequency measurements during contact. And lastly, we want to scan at a non-image, at a non-eigenmode frequency to minimize the cross-talking. All of these requirements are met in, as I said, in both force volume and peak force taping modes, but not in other intermittent modes like taping mode, AFM, for example. Here is showing an example of such measurements on a polystyrene polypropylene blend. Polypropylene is in form of this round area, is in semi-crystalline phase. The scan was 128 by 120 pixels over 2 microns area, was very slow, 1 second per ramp. And here showing maps of resonance frequency and resonance amplitude along approach and retract, different indentation depth going all the way from -5 nanometer out of contact to 5 nanometer into contact. Because the force volume was operated at a constant set point of 25 nanometers supply force, and there is a stiffness difference between these two materials. About beyond 2 nanometers indentation depth, the measurements were available only on polypropylene regions. So as we see, we have contrast not only in contact but also out of contact. So we can say something about the adhesive response of the two materials, contact formation, contact breaking, and this adds as new characterization dimensions to the measurement space of ICR AFM compared with CR AFM, which is strictly a contact AFM mode. In addition to such discrete sequences of constant indentation depth map, an even more complete visualization can be obtained in a 3D representation of data. because we know the 3D space location of each measurement, and here showing the tomographic cross sections along perpendicular planes and parallel planes to the surface in terms of frequency and amplitude, both on approach and retract. A closer look at the color contrast, for example, at the zero indentation planes, reveal differences between the dynamics of contact formation and contact breaking on each material and between the two materials. That give us more information about contact formation and contact breaking, right? We can convert this in three-dimensional representation of contact stiffness and dissipation, but we like next to talk about detailed analysis of the depth dependence of the contact stiffness and dissipation. For the contact mechanics analysis, we chose the Schwartz model, which is a transition contact model between the known DMT and JKR models. Unlike a DMT or JKR analysis that fixes the value of the transition parameter, either 0 or 1, with the Schwartz model, no a priori assumption was made for the value of the transition parameter, which instead was considered a free fit parameter. Also, in this, what we use in this analysis was that, as it was showing in the case of a fast oscillation indentation, the viscoelastic effects prevent the peripheral variation imposed by the oscillation onto the contact area. So in this case, we have more of a flat punch configuration with the contact stiffness proportional with contact radius rather than the slope of the force distance curve. So with this assumption of the flat punch configuration in the Schwartz contact model, we calculate the contact stiffness versus indentation depth, and the curves are plotted here, the dash and dot point curves, along with some measurements for each of the materials. We see a very clear separation between them. But even a better separation is obtained if we linearize this dependence, in which case the elastic modulus will come entirely from the slope of these lines and the transition parameter from the slope and the y-intercept. We also see that there are different values for the transition parameter here. So for polystyrene, they are more around 0.5, and for polypropylene, around 1. We perform this analysis at every pixel in the scan, and we end up with the maps for the indentation modulus and transition parameter. We see good contrast between the two materials. Polystyrene was used as a reference material with the elastic modulus 3.4 gigapascal. So polypropylene was 1.5 gigapascal. But interestingly, was also the transition parameter map. As we see the difference between these two materials, and the value for the polypropylene was around 1, and this shows a larger contribution from the short-range adhesive forces. And this contrast is better observed during retract than approach, this being enhanced by the difference in contact adhesion hysteresis of the material. An analysis also can be done, can be made in terms of depth dependence of the dissipated power. Here on top are showing individual curves of depth dependence of resonance frequency, amplitude, and dissipated power. On the bottom are plotted the same quantities along a scan line. So we have a colorful, nice distinction between the two materials, how they respond in during contact formation and contact breaking. If we look at the dissipated power curves here with red and blue, we observe comparable maxima in the dissipated power just before the contact is formed, but once the contact is formed, we see a distinct behavior with almost constant dissipated power on polypropylene and a monotonic increase in polystyrene. And it is conceivable that this is actually associated with the viscous response of the material, indicating that polypropylene is less viscous than polystyrene, maybe due to its semi-crystalline structure. On the retract curves, light blue and yellow, we can see that a large increase in the dissipated power accompanied contact rupture over about 4 nanometer for polystyrene and about 6 nanometer on polypropylene. So the idea is that overall this analysis indicates that during one approach retract cycle, a much larger amount of power is dissipated during contact formation and contact breaking than contact deformation itself. Now, to switch to the last topic, one impediment in force volume, as we know, it's that it's very slow. So the question is, can we make it faster? And the answer is yes, we can actually implement intermittent contact resonance AFM in peak force taping. And this is because in peak force taping we have all the requirements that we mentioned earlier are satisfied: force control during intermittent contacts, DC force measurements, force resonance frequency correlation during contacts, imaging at the non-eigenmode frequency, and it's important because in taping mode we don't have these ones. Taping mode is operating with feedback on amplitude, doesn't provide the DC force measurements, and operates at the first eigenmode frequency of the cantilever. The additional here is showing an example of this implementation with peak force taping operated at 2 kilohertz. There are also slower frequencies that you can modulate here. The slowest, I think, is 0.25 kilohertz. So anyway, for 2 kilohertz, right, we have a approach retract cycle happening in 500 microseconds, and on top of that we put a fast modulation frequency from a phase lock loop instrument, and here we see what happens. So outside of contact, the resonance frequency is that of the eigenmode of the cantilever used. In this example was the third eigenmode of the cantilever. Once we bring the probe into contact, we have a shift at higher and higher frequencies until the peak force, and then the resonance frequency decreases, and out of contact come back to the free eigenmode frequency. What I want to point here is that we apply these two modulations to the tip sample contact through two separate loops. The blue one is the Ph.D. modulation. It was applied on the Z piezo scanner of the AFM. The PLL modulation was applied on the piezo shaker of the AFM. So that's to minimize the cross-talking. And here is showing an example of such measurements. We have maps acquired both with regular peak force taping, topography, adhesion, dissipation, and modulus. This was done on a polystyrene PMMA blend. The polystyrene was the matrix, the PMMA, the cylindrical pillars here. And here, the last two maps are the resonance frequency acquired with PLL, either with a slow PLL or with a fast PLL. And just by looking at the color contrast, we see a correlation between the slow PLL map with the adhesion one and the fast PLL map with the modulus one. And the explanation is that with the slow PLL, in the maps that we are acquired, we basically get the average value. So with a slow PLL, because time constant is increased, we average a lot also over the out of contact regions, and this give us more contribution from the adhesive forces. So this is why this correlates better with the adhesive map. However, with fast PLL detection, we are able to track better the momentary what's going on with the resonance frequency. So here is a better evidence for this explanation, where we recorded successive taps by high-speed data capture with both slow PLL and fast PLL detection. So with slow PLL detection, we see here that the major shift in the contact resonance frequency are within 1 kilohertz from the free resonance frequency and with no significant force dependence. However, with fast PLL detection, the resonance frequency responds with fidelity to the force variation during each oscillation. Again, this is because with fast PLL detection, we momentarily track the changes in the contact stiffness and how this changes with the applied force. But this also points to the fact that only a three-dimensional characterization will be meaningful, being too complicated to separate the average contribution that are contained in two-dimensional maps. For quantitative measurements, we analyze the larger sequence of successive oscillation along a scan line, going over both polystyrene and PMMA regions. The contact model used was again the Schwartz model in the same flat punch approximation, but this time in terms of contact stiffness versus the applied force, we were able to linearize this dependence and plot the measurements both in the full contact region and in the region where the tip is detaching, the unstable region where the tip is detaching from the surface. And we fit both these two regions by keeping the same elastic modulus for a given material and let the transition parameters to be different from the full contact to the unstable region. So the numbers are here. Polystyrene was used as a reference material with 3.4 gigapascal. PMMA comes with 2.8 gigapascal. The transition parameters are 0.3 for polystyrene and compare well with 0.5 that we got before in force volume measurements. For the PMMA, the transition parameter is 0.1, close to DMT limit. And interestingly is also that the transition parameter show bigger values for the unstable region, and these large values are connected with the contact breaking events and indicate the predominant contribution of the short-range adhesive forces inside the contact. So this indicates that for contact breaking, we have a larger contribution to the work of adhesion from the short-range adhesive forces compared with that from the large-range adhesive forces. So my conclusions are here. We talk about depth dependence of contact stiffness in force control CRFM modes. We also talk about using flattened tips in these low dependent CRFM measurements, provide more reliable measurements and preserve the tip. Also, a better tip preserving is obtained in intermittent contact resonance AFM, and these are new modes that we can accomplish in force volume and peak force taping. And finally was this transition contact model, the Schwartz model, that provide an interesting analysis in terms of both elastic and adhesive properties of the samples. So with that, I switch to the last slide. And I guess Bede can say something about this one.
Sure. Yeah. Hello, everybody, and thanks very much, George, for co-hosting this here. Right. So George has brought up the very last slide of the presentation, where we actually wanted to make you aware of an upcoming advanced applications class that we'll have here in Santa Barbara, as well as our Nanoscale World Digest and Forum, where we often answer advanced questions very quickly. The slide also has Bede's contact information, and for any further questions, don't hesitate also to ask Bede directly. I was going to mention at this point again, after this webinar is over, you will receive a link for downloading it, and you might have also noticed along the way, for further reading, George has referenced some very interesting, very recent publications that go into further depth. So that said, I noticed we've received a lot of questions really at this point, and we're already far along with the time, but we will take the time to answer at least a few of them. So in fact, there was one question that came in about how technically we added the Z modulation into the peak force mode. And I know maybe, Bede, you want to say something about it quickly, or maybe George will say more on that.
Sure. Essentially, I want to remind you that this is not a commercially available mode right now. George has been doing some really exciting work to expand peak force tapping, but in order to do that, he had to use an external lock-in and signal access module to gain access to the dither piezo on the tip holder, and but basically just by he could use the AC signal from the lock-in to go to that tip holder, and then you can pull off the deflection signal out of the signal access module also, and then process that, and then take the output of the lock-in and put it into one of the front panel inputs on the Nanoscale 5 controller. So basically, yeah, this is the cutting edge, and we're happy to be able to provide the access to these signals to allow this possible this mode to be possible.
And there was a different question from a different member of the audience. Can this be, so with this approach, can this be done on a dimension icon in particular?
Yes, that could be done on an icon. You might want to examine what the best way to put the dither signal in would be, and to pull it out. The SAM-V is a little bit different from the SAM that George used, which is a multi-mode system that so he uses a SAM-3, but the SAM-V's got active electronics in it, and it's a bit more expensive, but still can work.
And another question came in about the range of material stiffnesses that you can detect in general and within a single map.
For peak force
in peak force QNM, I think a question came in early. It's probably referred to peak force QNM.
So so that's a very good question. Basically, in order to get our big range of material mapping, we use different probes, and so in order to do it within one map, you would not have the optimal probe for every material in your sample if you have a wide variation of material stiffnesses in the sample. So with peak force tapping, you might have a decade or so where you'd have reasonable accuracy in your sample stiffness. Actually, adding contact resonance to peak force tapping does allow a exciting possibility that one probe could be used with the regular peak force QNM force curve method of calculating the stiffness, but then also you could use the first and second eigenmodes to cover a much wider range of material stiffnesses, assuming that you can get good contact resonance for those eigenmodes.
Thanks, Bede. Yeah, another question was about the whether this could be done with a dimension 3100. And let me just say briefly, what you would need to do is upgrade to a dimension icon system to really open up peak force QNM. So the question with respect to peak force tapping in particular.
However, you could do the force volume version of this on a 3100. We had force volume available for the 3100, and so you could start out with force volume and then upgrade after you've decided it's really cool thing to do.
Right. Yeah. Specifically, the peak force tapping is one item where you need to go to the mention icon. Then there were a range of questions on looking at viscoelastic properties on a range of samples, on cells, on thin films. Also, there the question: how does the substrate affect viscoelastic measurements? Also on porous polymers. Do you have maybe answers to some of these?
Yeah. So the DMT model that we use is very simple, and it only covers elastic behaviors, and it uses one extreme of the adhesion possibilities. Gheorghe has expanded that to use his Schwartz model so that he can cover the range between JKR and DMT, which allows you to better deal with exactly how adhesion is affecting the measurement. But none of these methods that we've applied so far or talked about have directly calculated viscoelastic properties, and there's definitely more work to do there. But contact resonance does have some promise. Also, we can observe variations with the force curves, as I showed. So I mentioned that because so firstly, viscoelastic properties are not calculated currently by either one of these. So that's the first thing. Second thing is when you start putting geometries like porous and thin films into the equation, if you're talking about a very thin film where it really is thin compared to the deformation depth, then those will require additional models. Both of these techniques allow you to acquire all of the data so you could go back and fit it with your own models, assuming you have one. And then I guess the last thing about the cells, viscoelastic properties of cells in there, when you start operating in fluid, things get a little bit more complicated. In some sense, it's actually better because usually you have less of an issue with adhesion. But you also have to deal with the fluid and the environment that the cell requires in order to live. And so basically you have to worry about the background viscoelastic signal that's coming from the cantilever. There are various different things that can be done to deal with this. The simplest thing is just don't go to too high of a modulation frequency. So, for example, we have an application note out there which talks a little bit about viscoelasticity and measurements on cells. If you send me an email, I can send you a copy of that application note. But we worked at 250 hertz on that one, even though we're using peak force QNM. We were not able to work at 2 kilohertz for those samples just because the viscous background was too high. So.
Yeah, and I was wondering, Gheorghe, did you have anything to add on your samples, the influence of geometry of the sample that you did or didn't have there? Anything you would want to add, Gheorghe?
Well, the contact geometry is very important in the analysis of the measurements, and either we consider it's a large range of what kind of sample we can have. We can go from nanowires or nanoparticles. We can have sample with higher roughness or granular structure. So it's the simple way is to use the known analytical contact models, but I mean, ideally would be if we can do a modeling, a finite element modeling of the sample, but this is very time-consuming and difficult. But the things are evolving very quickly. So in the next years, maybe we will see big improvements in the contact analysis that we need to do.
Yeah. Thanks, George. And maybe just one comment I should also make in general that affect the answers of these questions. One of the more recent additions on our side on just peak force tapping has been the peak force capture function, where you capture and download the complete force curves for all of the pixels in the image. It's very, very analogous to what you do in force volume, so that you do have the complete raw data and can apply different models as needed. Now, there was a question earlier on the DMT model and the effect of adhesion in your modulus measurement. Bede, did you want to say something to that?
Yeah, I mean, the DMT model is a very simple approach to the calculation of modulus, and it does include adhesion. It is not. It doesn't specify where that adhesion is coming from, but and it is one extreme of the way of possibly treating adhesion in the measurement. The JKR method is another way. And the Schwartz model, which George has talked about, can actually span the two, which is a nice way to go. So currently we can calculate the real-time DMT modulus. We cannot calculate any other model for modulus currently, but in real time. However, as Thomas mentioned, we have those peak force capture files, so we can acquire the force curves, and then they can be fit separately with MATLAB or something like that.
Another question came in on the separating out topography effects in the modulus adhesion deformation images. Any comment on the effect of topography and what one could do to separate it out or minimize it?
So, I mean, in contact resonance, for example, it's possible to correlate the two maps, the contact stiffness and topography, in the case when topography is not a flat surface, right? So then use a self-consistent analysis to separate these two contributions, but also I didn't point out, for example, in that granular gold film, I also considered the lateral couplings. So the contact geometry is more complex, but could be separated if you have more information in terms of topography and try to mimic the real contact configuration that might be there on your sample.
Do you have anything to add, Bede, on topography?
Yeah, I mean, one of the big ways that topography shows up in these techniques is that when your tip is interacting, the edge of your tip is interacting with the edge of a feature on the sample, and you'll see in your property maps, you'll see those variations. And that's one of the nice things about having property maps that can actually be correlated very easily to the topography, because you can immediately look at it and say, well, that's changing because I'm on the edge of something. And usually the way I try to get around that is I try to find areas where it's on top of the feature, or so it's relatively similar to the model calculation, which is a flat with a sphere, right? So if you have samples where you cannot do that, for example, say your tip is actually relatively large compared to some of the features that you want to measure, then you need to think about the possibility of either turning that calculation around and using like a sphere thing, or finding some different model that could actually allow you to look at the behavior of the the geometrical structure.
So I think that is always a very important question in AFM, that question of topography. In part, maybe our approach is we provide all the information at the same time so that all the information is there to correlate. It was in that sense particularly interesting also the example that Bede showed early on, where there was actually not a change in the nature of the topography across from one layer to the next, so that you couldn't even see the layer transition, yet you saw the change in the property, and in that sense that change was probably not topographically induced, in that there was clearly no correlation to the topography in that jump in a modulus there. We have a lot more questions here, and I think some of them require more detailed answers, but are actually way over our time for the webinar. So we'll conclude this webinar at this point. I want to thank you again for your attention. Please don't hesitate to contact us directly. You will have seen, and will also see in the presentation, that you can download Bede's direct contact information. You'll also see some interesting recent publications cited there for further information. And with that, I thank you for your attention for this webinar, and look forward to more interaction with you. Thank you. Bye.